Alright, hey guys, what's going on? So today we are going to be talking about light cone coordinates. These are going to be really important later on when we talk about string theory because this helps us understand our Minkowski metric and our space-time interval in a different way. So let's go ahead and get started. So we're going to define two new variables, but they're not really new variables. It's just a new way of sort of collecting two objects together, okay? And these two objects that we're collecting are going to be the time component, so the time component and the x1 component. Now you could say, well, we can merge x2 also. The point here is that we're going to use light to sort of reparameterize time, okay? Or time to reparameterize light, however you want to say this. But the idea, again, is, and we'll go through this in quite detail to make sure that we understand it, is that we're really merging the direction that the direction that a particle is moving to be the direction of time as well. So this is sort of, again, a way of reparameterizing light particle, okay? So the complete set of coordinates in four-dimensional space then is going to be instead of the x0, 1, 2, and 3, we have x plus, x1, x2, and x3 now. Okay? Because we use 1 and 0 up here, but not 2 and 3. So these two guys are now different. We still have four components. Okay? But they're different, right? This is x plus, x minus instead of x0 and x1. So this is to say that at every point, you have some space-time, and you have some vector. This vector, instead of having x, y, and z components, right? So it has, say, t, x, y, and xy components and z components. Well, now it has, instead of x and t, right, instead of x and t, here was our t, here's our x. We now scratch these guys and we say one is going to be x minus, the other one's going to be x plus, and these two are linear combinations of x and t, right? So it's a weird way of thinking about this, but it's going to help us in understanding something. And we'll get to that something later because we want to understand that all four vectors, not only do they have components in t, x, y, and z, but they have components in x plus, x minus, x2, and x3 also. It's just a coordinate trend. It's somewhat of a coordinate transformation, if you will. Okay? And so this is what that looks like. So all four vectors we're saying have these components. And we can see that when x minus equals 0, multiply both sides by square root 2, we get this, and then bring this to the side of the equation, we get x1 equals x0, which is interesting, right? The way we parameterize time is the same way we're going to parameterize the x coordinates, okay? Similar here with this guy, this is just the negative direction of the x components. So this is, if we're defining in our standard Cartesian coordinate system, this side is the plus side, this side's the minus side. This is the thing with the negative slope, right? So we have negative slope, and this is the thing with the positive slope. Positive slope here. We have a positive slope right here. All right. So, okay, that's all fine and good. This is still kind of abstract, but it's abstract to the point where we'll be able to use it quite usefully in string theory. All right. So the product of these two coordinates recovers the Minkowski metric. So if we multiply the two, we multiply, here's our plus, here's our minus, here's plus and minus, and we multiply all this out. Okay, we cancel out our square root 2's with our 2 right here. And then these guys will cancel, right? And so we get this. So we can rewrite our line element then as this being these two guys, and then we have the other two here, right? So And this has that sign, this has a positive sign, a negative sign on x1, negative on x2, negative on x3. So our line element, I don't have our line element here, but our line element, it was in dx0 squared minus dx1 squared minus dx2 squared minus dx3 squared. Right, this part here is this bit right here, right? All right, but this is not the only way we can do this. We can do this for, we can also do this if A and B are two arbitrary 4 vectors. We can do this multiplication, which is right here, and then this multiplication, which is right here. Find this, we're sort of finding the sum, but both of them are going to be negative. Okay, so it's the negative sum. And so we get the this guy here, right? So this times this is given us right here. Then we have the minus sign. So, and we can do all this multiplication. We get this. The greens are going to cancel. Reds are going to cancel. We get this guy here and this guy here. That's going to go to minus 2 times A0, B0. And then we have A1, B1. That's going to be a 2 there. We could see now why we have these square root 2's in here is because when we do this, and similar to when we do this, right, these square root 2's are really just here to cancel out. And so we get our invariant back. And so we have this, and that leads us to this right here. And so if A and B were just the x coordinate, we could say that this here then is equal to x0 squared, right? Because we're just using x, right? So we just put x in here, x in for here, and so we get the same thing. So we can write the Lorentz invariant like this now between any two 4 vectors, any two arbitrary 4 vectors. All right, for a particle moving in the direction of light, we write that the position of the particle, x1, is its velocity multiplied by the amount of time that has passed, which is v of t. This can be generalized in special relativity to beta times x naught. Again, x naught is the t component. Beta is v divided by c. C is usually 1 when we're working in special relativity, but this is a generalized notion. And so x plus then is going to be this, as we said, but this was x1. This is x1, so we placed this in for x1. We get this. We get this for the minus portion. All right. So dx plus dx minus equal these two guys, right? Because we're just multiplying things out. Because now we have common x naught terms. Okay. And same thing here. Taken together, we could say that dx minus, we have the 1 minus beta, over dx plus, here, it's right here, because x zeros are going to cancel out. These two guys are going to cancel out, so we get 1 minus beta over 1 plus beta. This is the light cone velocity of a particle. I should probably bold that, but this is the light cone velocity of a particle, where dx, we're going to say now that dx plus is dt, right? So we get, this is the derivative then, dt of dx minus, okay? And that's important because we need to make a choice later for what our, when we do momentum, when we're working with momentum, we're going to have a P plus, P minus, P2, and P3. We've picked dx plus to be the temporal component. This is the temporal component. So you would think maybe we should pick dx P plus here to be the temporal component of our momentum in this new coordinate system. But that's not going to be the case, and we'll see why in the next video that we want to choose this guy. But let's go ahead and continue. So as the velocity of so we could see according to this equation that as the velocity of the particle increases, the beta factor increases, which means that the numerator it decreases, and so the denominator increases. And so this corresponds to the light cone velocity of the particle getting closer to zero. It's for this reason that we're going to call the plus, x plus, the light cone time of the particle. Okay? So as a particle travels faster and faster to the speed of light, it gets closer and closer to our this line here. This line here, again, being the speed of light. This is of the 45-degree angle light in our space-time. Okay. So if beta is negative, I make some of these typos sometimes. If beta is negative, theoretically the structure of special relativity is not violated, but the light cone velocity of the particle is infinite, right? Because if this thing is negative, then our denominator here is going to be 1 plus something, and as it gets more negative, that's just going to, this thing is going to go to infinity, essentially, right? So in these coordinates, therefore, there is a means by which particles can have infinite velocity, okay? That's just something to note. We'll come back to it later. So let's talk about some relativistic energy and momentum now, because we haven't talked about that yet. We need to in order to continue. So we're going to say that the form momentum of an object, now you might have seen this in my quantum field theory playlist as well. We're going to recapitulate it here. I want these playlists to be somewhat self-contained, so I'm going to try to avoid saying refer to my playlist over here, refer to this playlist over here. Everything's going to try to be relatively self-contained in this manner. So we're going to consider this to be an invariant line element for our momentum. This the mass times the velocity squared of some particle. Okay, in the case of light, that's m squared c squared. Okay, and so we can lower the index again with our Minkowski metric, and when we do that, we get this here and this, right? So this here is excuse me. This thing here is our p mu, right? And then this thing here is our p mu, and we have our Minkowski metric. Okay. Okay. So we can multiply Minkowski metric by this, so we get all these relevant negative signs, and then we have this, and then we get this, right? Where this thing has a positive sign, these three guys have negative signs, so we can package all this into a vector that looks like this, and so we have our temporal component and our three spatial components packaged into this vector. If the particle has zero momentum, then we have this guy right here, right? So this guy here is so we set this to 0 if it has zero momentum, and we get this. We multiply both sides by c squared, and we get this when we take the square root. And this is the famous Einstein's relationship, right? E equals mc squared. And so we've shown that then this is our 4 momentum, and our 4 momentum vector invariant is this guy. Okay. So for a particle moving along the x-axis, recall that the time dilation looks like this, right? So we have ds, this is dt and dx, for both of them again have opposite sign. And if it's moving in dx, well, we can rewrite it in this way, where we've talked about this is the gamma factor, right? But because we're moving in x, we can rewrite it like this, okay? Where the gamma factor contains the velocity moving in the x direction. All right. So taking the square root of both sides, and we'll see also why this works, right? When we take the square root of both sides, well, we get ds, right? So equals c dt, taking square root of these guys, square root of this, okay? Well, this then is just gamma, right? So we could say that dt ds, right? So we divide both sides by ds, so we get this, and then we get we divide both sides by ds. We're going to get 1 over here, and we can then we get 1 over gamma, right? So 1 over gamma, that equals gamma, right? Because gamma, as we've said, was 1 over 1 minus b squared, right? So that's how we get that. And then we divide by c, right? Because when we divide by c, because we're dividing both sides by c here, right? So this here, so you can really just stare at this, right? If you stare at this for a few seconds, you see how we get this. Right? Not too difficult. So therefore, we can say that ds, or dx ds, is dx dt dt ds, right? Because that's just, you can cancel those guys out, and we get this here, right? Because dt ds, we said, was this gamma over c. Dx dt is this guy right here, okay? So from there, we can say that the velocity 4 vector of some object at any point in space-time is this, okay? So if we say this, right, so if we say this, and if we say this, right, so these are sort of the ifs, right? If we say this here is equal to this, and if we say this, then we can conclude that, well, d mu ds, or dx mu, that's so dx mu ds is all equal to this, right? Because we have the temporal component with respect to ds, dx, dy, dz, all with respect to ds. Okay. Again, because that dt cancels out. And so we get this right here, and we're able to throw this gamma in here because it shows up right here. Okay. All right, so we can conclude that we can conclude this, and so this is the relativistic 4 velocity of a particle. We can see that from equation 8 and 11, right? So this guy here and this guy here. We can recover all these things here, right? So really what we're saying here is that if we stipulate this and if we stipulate this guy here, then we are able to get the Lorentz transformations back. Okay? Recall the 4 momentum of an object. Is the object's mass multiplied by its velocity. This confirms that the velocity is a 4 vector, so we can take the equations that we learned from the last section. Okay, so the last section here, we got these equations, and from those, we can rewrite our energy and our momentum in this way, right? Because px is dx, and then E over c, that is our, we said, is our temporal component, right? So that's this temporal component here, right? A simple thing that I use to understand what's going on here is knowing that beta, again, carries everything we need to know about the velocity of some moving frame. And so now we want to put all this together, okay? I decided to make this a separate video from what the next video is going to be. The next video is going to be taking the light cone coordinates and applying those to energy and momentum, okay? And then from there, we're going to be able to take a look at we're going to start looking more at string theory stuff, right? So these first few videos are just going to be a review. We're going to then start diving into more quantum stuff and more trying to hint more and more towards string theory. So with that being said, make sure to hit the like and subscribe button. Make sure to go into my Patreon page to support me there if that's something you're interested in, or you can also become a member here on YouTube. Whichever floats your boat. I'll see you guys in the next video.